This is 12.1.4. Millikan's determination of electronic charge E. So Millikan did a few experiments, and through these experiments he figured out what the charge of an electron was. So first let's start to construct what his experiment looked like. So first he's got metal plates which are charged, and then attached to there he's got a little spray nozzle. And when he sprays oil, which becomes charged. When these oil droplets become charged, as they're falling, they experience two forces. One force they experience due to gravity, so mg, but because they're negatively charged, they experience another force, which is that they're attracted towards the positive plate. So we'll draw our little oil drop, and I'll put a few negatives there to show that it's been negatively charged. They could be charged by only gaining one electron, but oftentimes they could be charged by gaining multiple electrons, hence why I've done multiple negative signs. So it's got Mg going down and Fe going up. And what he could do is he could adjust the electric field between these plates, again by adjusting the potential difference, until he manages to get an oil drop to be suspended in the air and not fall. And he would observe these using a traveling microscope. So there are two ways of charging these oil drops. They can become charged naturally just by the act of spraying them because they experience some friction, or you could charge them using alpha particles. So charging oil drops can happen naturally during spraying, or you could use alpha particles. Difference here being if you were to use alpha particles to ionize them, then they'll be positively charged instead because they'll have their electrons ripped off. So you'd have to adjust the electric field to account for whether the oil drop was positive or negative and to suspend it. So it just means flipping the plates around, or the polarity of the plates. So Millikan adjusted the potential difference until he caught oil drops in suspension. So at that point, we've got the electrostatic force and the gravitational force in opposite directions, and they're equal to each other. So if we've got our oil drop, we've got Fe and Fg. So Fe is equal to Eq, and Fg is equal to mg. So at this point, he knows that they're equal to each other. So we say that EQ equals to mg, and E is V over D from electric fields. So that means that we've got QV over D equals to mg. Put a box around that. So if we wanted to determine the charge on that oil drop, we need to know the mass of that oil drop. So mass of oil drop needed to determine Q. So this is actually a bit of a problem because we don't know the mass of an oil drop and they vary quite significantly. It's not very easy to measure the mass of a single drop. So what Millikan did next is he allowed the oil drops to fall and reach terminal velocity. So they stopped accelerating. Now it's very easy for oil drops to reach terminal velocity, or any spray for that matter. If you were to spray air freshener, for example, and just look at all the little particulates, they reach terminal velocity quite quickly and then they sort of just fall very slowly because they have very small mass. So it doesn't take a lot of force for them to reach terminal velocity. Start a new page. So oil falling under terminal velocity. So Millikan allowed the oil drops to fall, then he timed it in order to calculate their terminal velocity. So as I said earlier, they have small enough mass that they reach terminal velocity very, very quickly. So we can assume that they reach terminal velocity almost instantly. So oil drops have small enough mass such that they reach terminal velocity very quickly. So in order to do this, in a practical sense, if you have your plates sufficiently far apart, if you turn the electric field off, then you allow the oil drops to fall under gravity and then they reach terminal velocity very quickly. And then if you time it by a known distance, you get time it takes to fall by a known distance, then you can work out the speed. So we're going to assume that the oil drop is at terminal velocity for the entire duration that it falls, because we said it reaches terminal velocity very, very quickly, so we can say that it's basically reached terminal velocity almost instantly. So assume oil drop falls at terminal velocity for the entire fall. So in that case, V is just equal to S over T. So he can easily measure the distance, he can easily measure the time. That's not very difficult, especially if they're falling rather slowly. Now, at terminal velocity, you've got two opposing forces acting. So, in the very beginning, the moment the oil drop begins to fall, it's only got one force acting on it, which is mg. And very quickly, it gains drag, which becomes big very quickly to the point where it equals to mg. So the oil droplet only spends a very small amount of time to accelerate and then falls at that velocity for the rest of the time. So we can say that the time spent accelerating was negligible, but it still did spend some time to accelerate, so it did accelerate almost instantaneously. So at terminal velocity, our oil droplet has mg going down and an equal amount of drag upwards. At that point, the two forces are in equal magnitude but opposite directions. The resultant force on the oil droplet is 0. So according to Newton's first law, it carries on at constant velocity, which is the terminal velocity. Now the equation for drag comes from Stokes' equation. This is a new equation for you guys, which is F is equal to 6 pi eta RV. Put a box around that. Eta is the viscosity of the fluid that it falls through. In this case, it's going to be air. So eta for air is equal to 1.84 times 10 to the minus 5 kilograms per meter per second. And this value will be given to you. So now there are two things that we need to find out. We need to find out what mass is, we need to find out what R is, because these two things with the oil drop we don't know. All right, let's start a new page. Finding M and R. So we're falling on the terminal velocity. Which means that mg, its weight, is equal to 6 pi eta RV. So we know the value of g, we know eta, and we can measure the velocity very easily. At the moment we don't know mass and we don't know R. So both M and R are unknown. We make another assumption that our oil droplets are spherical. So assume oil drops are spherical. So the mass of our oil drops can be given by the density of oil which we know, we can look that up, or we can take a bucket of oil and measure it very simply, and the volume of each oil droplet. So mass is equal to rho times V. And because the oil droplets are spheres, the volume of a sphere is given by 4 over 3 pi r cubed. So if we substitute both of those together, we get that the mass of the oil droplets is equal to 4 over 3 pi r cubed rho. Now if we take that mass, 4 over 3 pi r cubed rho, and we substitute it back into mg at the top, we get 4 over 3 pi r cubed rho equals to 6 pi eta rv. Now we have an equation that only has one unknown in here, because 4 over 3 pi, well that's just a number. R cubed and R, they're on both sides, but we can rearrange that. So we want to find what R is. The density of oil, well we know that, or we can find that out very easily. 6 pi is just a number. Viscosity of air, again you can look that up. And the velocity of the oil droplets, we said that that's fairly simple to measure, so he could measure all of that. Ah yes, I forgot to put G. There you go, G. And again, G is known as well, 9.8. So at the moment, we've only got one thing in this equation we don't know, which is R, and it's one of the things we want to find. So then we rearrange it. So if we rearrange that, we get R squared is equal to 6 pi eta V over 4 pi rho G, and then the 3 goes at the top. So 6 times 3, that's 18. 18 over 4, that's 9 over 2. So 9 pi eta V over 2 pi rho G. The pi's can cancel out. And that's equal to R squared. So if we square root it, we get R is equal to the square root of 9 eta V over 2 rho G. Put a box around that. We've now found the radius of the oil droplet. So R is now found. Which can be used to find the mass. So mass was given by rho V, which is 4 over 3 pi r cubed rho, and R was found to be the square root of that, so let's just substitute that in. So mass is equal to 4 over 3 pi brackets 9 eta V over 2 rho G. Because it's square rooted, that's to the power of a half, then power of a half cubed is power to the 3 over 2 rho. Put a box around that. We now use that equation to find the mass. So now M is found. We can go back to find charge. of oil drop. So go back to our equation, QV over D equals to mg, and we find that Q equals to mg D over V. So now we found the charge of the oil drop. So Millikan repeated this over and over and over again. He found the charges for many, many oil drops. And then he started analyzing his data. In his data, he found that charges of oil drops only ever increased by 1.6 times 10 to the minus 19 coulombs. So there was never any difference of anything less than 1.6 times 10 to the minus 19 coulombs. And every single value of charge that he got was an integer multiple of 1.6 times 10 to the minus 19 coulombs. So from that he gathered that the smallest possible charge that you could have was 1.6 times 10 to the minus 19 coulombs. So let's write this down. Millikan obtained results for lots of oil droplets the value of each of these charges was always an integer multiple of 1.6 times 10 to the minus 19 coulombs. So he concluded that 1.6 times 10 to the minus 19 coulombs was the smallest possible charge you could have. And because there were no steps that were less than 1.6 times 10 to the minus 19 coulombs, for example, you couldn't go from 1.6 times 10 to the minus 19 to 2.0 times 10 to the minus 19. The next possible step in charge was from 1.6 to 3.2 times 10 to the minus 19 coulombs, which meant that charge was also, not only was there a smallest possible value of charge, but that charge was quantized in that it only increased in those steps. And that charge was quantized. And so we bring all of this together. We know that our electrons, the cathode rays, were negatively charged. So we know that the smallest possible magnitude of charge is 1.6 times 10 to the minus 19 coulombs. So if that's the smallest magnitude of charge and that electrons are negatively charged, then the charge of the electron was negative 1.6 times 10 to the minus 19 coulombs. And that's the end of 12.1.4.